Vani, and I'm explaining the first part of our assignment, which is piezoelectric speaker. This is a signal generator through which we have given a signal to the speaker and the oscilloscope through a breadboard, and we have taken the output from the speaker to the oscilloscope directly. So here, as you can see, we have our input wave, and if we increase the frequency of the wave, simultaneously the sound from the speaker changes and the waves here change as well.
Okay, done.
There is a maximum frequency to which sound from the speaker is coming. Like, for example, in this case, the maximum frequency is 17 kilohertz, after which the sound from speaker does not come, yet we can still see the waves on the oscilloscope.
This graph represents the phase difference versus frequency of a piezoelectric speaker experiment, showing how the output signal lags or leads the input signal at different frequencies. At low frequencies, the phase starts as minus 180 degree and gradually shifts towards 0 degree. In mid-frequency range, the phase fluctuates between 0 degree and 100 degree, suggesting complex response behavior. A sharp phase jump occurs at 2500 Hz, where the phase shifts from plus 150 degrees to minus 150 degrees, making a strong resonance point where energy transfer is most efficient. Degree phase shifts are characteristics of piezoelectric resonance, crucial for filter design and frequency resonance analysis. The most prominent peak in the FFT graph is at 1.3 kHz, which is likely the resonance frequency of the piezoelectric sensor. At this high frequency, we are able to know that piezoelectric material is responding strongly at this frequency. The strong peak at 1.3 kHz suggests that this is a resonant frequency of a piezoelectric material. This graph helps to identify the frequency response of piezoelectric system, useful for vibrational analysis and ultrasonic applications or stress sensing.
Hi, I am Shubham and I am going to explain about second part of assignment, that is magnitude response and phase response. This is signal generator and this is oscilloscope. The signal generator is used to generate sinusoidal signal, and this is oscilloscope, which is used to compare input and output voltage. This is our circuit for analyzing the frequency response of a photodiode, and we are using LED as our light source driven by signal generator and photodiode connected in reverse bias mode, which ensures will generate small amount of current. Now we measure input voltage on channel 1, and output voltage on channel 2.
The graph is V output upon V input versus frequency. This graph illustrates the gain as a function of frequency. Frequency in kilohertz is represented on x-axis, whereas the y-axis shown the V output upon V input, determined using formula 20 log V output upon V input. Now we are able to see that at lower frequencies, the V output upon V input stays fairly consistent. As well as there is a rise in frequency, the value of V output upon V input begins to decline consistently, suggesting a filtering effect. This type of behavior of frequency As long as frequency rises, the value of your output upon V input begins to decline consistently. This behavior is anticipated in a system where circuit properties like capacitance and inductance lead to attention of higher frequencies. Now our next graph is frequency versus phase difference. Ultimately this graph illustrates the phase difference as a function of frequency. We are able to say that frequency in kilohertz is plotted on x-axis and phase difference is on y-axis. The phase difference begins at 0 degrees for low frequencies and gradually increases as the frequency rises. This type of behavior shows that the output signal progressively trails the input signal as frequency rises.